Welcome back. Today we're going to be looking at power functions and polynomial functions, section 5.2. This is coming right on the heels of quadratic functions, so what we're going to do today is just look at what happens when we go to the next power. So we started with linear functions in 4.1, the power with x to the power of 1. We moved on to quadratic, x to the power of 2, and now we're going to see what happens when we expand this to 3, 4, 5 p powers. So without further ado, let's go ahead and get started. Pretty simple definition as we start. We've got ourselves a simple term, a single term, a monomial, one term, with a coefficient and with a power, or an exponent, right? And that's it. So when you're looking for a power function, you're looking for a monomial that has a coefficient and an exponent. So what we're going to do first is we're just going to, can we see these? So let's look at this thing and say, ooh, is this or is this not a power function? Well, they're trying to trick us by putting this times sign, but we know that multiplication is commutative, so we could take that 4 and that 2 and multiply them, take that x and that x to the third and multiply them, end up with x to the fourth and say, yes, it's a power, because we can combine those like terms. But when we get over here and we see different exponents, they have to have the exact same exponent and the exact same variable to combine. They do have the same variable, but they don't have the same exponent, so they cannot combine. These are not like terms. And so this is not a power. Technically two powers added together, which we'll get to later when we explain polynomial functions. Last but not least, we know what this is, not a power. This is a rational function. It's got an x on the bottom. We'd have to have a domain restriction, so no, it's actually rational. All right, so power has to be a monomial, a one-term function that has a coefficient, even if it's 1 and invisible, and a power. The reason this is so important is because we want to look at end behaviors of functions, and in order to look at end behaviors, we look at the leading term. We look at the leading power function, or the leading monomial, and we say, okay, there's 4 things that could happen. That leading term could be positive or negative. If it's positive, you're going to have a smile with the broken up middle, or you're going to have an increasing bank account if you go from left to right. So I imagine those 2 things. If I'm happy, my bank account's going up, that's a positive thing. If it's a negative, that first coefficient's negative, I'm sad, I'm frowning, or my bank account's going down. So that's the first thing. You look at the sign. So let's go up here. I'm going to look at right here. I'm going to say, what was the sign there? The sign was positive. That means it's either happy or an increasing bank account for the end behavior. Now I'm going to look at the exponent and say, is the exponent odd or even? Well, if it's even, they're going the same direction. The way that I like to remember that is think of the easiest even exponent you can. I think that's x squared, and we know x squared looks like a parabola. Whether it's up or down, x squared is a parabola. So even, think of the easiest even, that's a parabola. The end behaviors go in the same direction. If it's odd, think of the easiest odd you can. I think that's x to the first power, and that's the normal line. So that's kind of how I like to remember which direction the end behavior is going. All right, so let's describe the end behavior here, describe it in words and in symbols. First thing I'm going to do is look at this coefficient. I see that it is negative. Negative means I'm either a sad person or my bank account is going down. So that's what that negative coefficient means. Next, I'm going to look at the exponent, and I'm going to see it's even. Even means it's like a parabola, so that means it's either going up or it's going down. Now what I'm going to do is I'm going to look at these 2 cases and say, okay, which one is it then? What do they have in common? Which 2 are in common here? The 2 downward facing looking parabolas are in common. And so the way I like to symbolize this is draw a down arrow, dot, 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 because we don't know necessarily what's happening in the middle. It could be the craziest function in the world, and we don't necessarily know what's happening. And then on the other side, it goes right back down. And then in symbols, the way we say this, if you look up above, you can see as x approaches negative infinity. So technically what we just said, as x approaches negative infinity is like that, right? Then what is y doing? Y approaches negative infinity. It's going down. And as x approaches positive infinity, y approaches negative infinity. It's also going down. Cool. So there's words. There's symbols. All right. Well, that's it. That's it for power functions. Now we move on to polynomial. Now we say, well, what happens if you add 2, 3, 4 infinite of these things together? Well, you've got a polynomial function that we need to establish some things about. So we're going to say this orange section is the leading term. The first term, the highest degree, the highest exponent is the leading term. The degree is the exponent of that leading term. The degree in this case is n. The leading coefficient is that whole coefficient, including the positive or the negative sign. The leading coefficient right there is an. Cool. So, not too bad. We're kind of taking baby steps as we get through here. Identify the degree. I'm going to do that in red. The degree, I look at the highest possible. Maybe I'll rewrite this first, and then we'll look at the highest exponent. So rewrite it. Put the highest exponent in the front. Now, the 4x squared. After that, the 2x. After that, the 6. And I'll say, okay, what's the degree? What's the highest exponent? The degree is 6. Okay, what about the leading term? Well, the leading term, sometimes I'll write LT. The LT is that whole clouded term, negative 6x. The leading coefficient, we can do orange. Leading coefficient is just what's in front. That's just what's right there. Even if it's an invisible negative 1, the leading coefficient is negative 1. And that's all they asked us to find. The reason they asked us to find this is so that we could identify the end behavior. I'm going to go ahead and do that. I see that it's even. That means it's either going up or down. That's because it's even. And then I see that it's negative. That means that I'm a sad person because my bank account's going down. And so I circle that and say that's the end behavior. The end behavior looks something like that, even if we don't know what's happening in the middle yet. All right. Now we're going to go backwards. Say, hey, here's a function. Determine the end behavior. Well, we get 1, 2 end behaviors happening right there. As x approaches negative infinity, or as x goes that way, what is y doing? It looks like y is also approaching negative infinity, going down all the way. And then as x approaches positive infinity, it looks like y is still going down to negative infinity. Okay, so that's the end behavior. Boop, boop. We call that end behavior. Determine a possible degree. See, notice they didn't say the actual degree. It's because it's really kind of hard to know without any information, without any exact information about the thing. We can say we know that it's either 2 or 4 or 6 or 8, and it's even. My guess is, because based on memorizing those toolkit function, it looks like 4. But the possible degree, I would say it's 2, 4, 6 is a good possible degree. So possible degree, we would need more information to find the actual degree. Because we might be able to horizontally shift this or make it look really similar, even if it's not exactly the same. We would need some sort of given information, like a couple points. We would need maybe a 0 or 2. I can't tell if that's an exact 0 at 1 or not, so I'm not going to go ahead and guess and say it is. All right, let's keep rolling. Characteristics of polynomials. This is very similar to what we've talked about earlier with increasing, decreasing sections. We've talked about turning points. We've already talked about x-intercepts. We've talked about how to find x-intercepts by saying f of x is equal to 0. We talked about how to find y-intercepts by saying f of 0. We talked about turning points and how these can be maxes or these could be mins. They could be local maxes. They could be local mins. We've talked about all that when we did characteristics of a graph. Now we are going to jump straight in and find these things using some tools that we've already have from previous sections. So the first thing we're going to do, I'm going to do the easy one first because I like to. It says determine the x and the y-intercepts of this polynomial function. Y-intercept's easier. Let's do y-intercept. Remember the y-intercept formula is you just plug in 0 for x. If you plug in 0 minus 0 minus 0, you get 0. And so we've got our y-intercept of 0, 0. That's not too bad. If you want to see that, 0, 0, 0. That goes away, that goes away, that goes away. And we're left with 0, 0. Fun little fact, they gave us an x-intercept right there too by doing that. We've got also an x-intercept. So we've got one of the potentially 3 x-intercepts. All right, now we'll find the harder one, which is the determine the x-intercept. So now we'll do the x-intercept, and how do we find an x-intercept? We set the whole thing, I'll just start right where they gave it to us, equal to 0. Say, okay, well, how are we going to solve this somewhat long equation? It's cubic, and it ends with an x. In order to do this, we need a factor. If you remember the first step of factoring is see if there's any like terms. So I'm going to pull out a 0, and I'm going to say what is a common between every single term. We got 2, 6, 20, so maybe a 2. We got x, 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 maybe an x. So let's see, if we take out a 2x and we reverse distribute, it's like the distributive property in reverse, or we factor out a 2x. The 2 goes away and we're left with x squared minus 6x. Nope, because we took out a 2. Minus 3x minus 10. Ooh, and now we've got a quadratic that we can factor. So we're going to look at that in the normal way that we factor quadratic equations. We're going to say, is there any factor of negative 10 that adds up to negative 3? What about negative 5 times 2? Seems to be good. So we've got our 0 equals 2x. That's staying out by itself. It's already out there. In fact, it's giving us this 0, 0 that we've already found. X minus 5 and x plus 2. And if you remember, how do we use these to solve for zeros? We set each individual term equal to 0 from the zero product property. And so if you set 2x equals 0, you get x equals 0. If you set x minus 5 equal to 0, you get x equals 5. And if you set x plus 2 equal to 0, you get x equals negative 2. And we got ourselves 3x intercepts. So over here, I'll write the O in blue. We said blue. The x-intercepts were 0, 0. That's the same as the y-intercept, and that's okay. 5, 0, and negative 2, 0. Awesome. So we determined some x and some y-intercepts using factoring from previous sections. We could go to a graph even. We don't need to do this whole thing because we'll get to graphing later. But if we wanted to go to a graph and plot those 3 points, 0, 5 way over here, maybe negative 2 right there, and we knew the in behavior. This is just me getting carried away with some math because it's fun. They didn't ask us to do this. We know the in behavior because it's going happy, because it's positive, and opposite. And then I know we don't know about crossing and multiplicities yet, but we could imagine it probably looks a little something like that, perhaps. Maybe it's a little different, but once we hit multiplicities and we see that each of these has a multiplicity of 1, this is a little teaser for next week or the week after, we'll see that each one of those crosses and we get a quadratic or a polynomial that looks something like that. Maybe. The y-intercept helps a lot because we already know the y-intercept, so we know that that flows right in line with that y-intercept that we had, and we kind of got a rough sketch of our graph. All right, let's look at this one principle of turning points. Turning points, so we just did a little sketch of that graph for fun, and we look at that graph and we say, hey, I noticed 2 special points. I noticed a local max and a local min right there, and it looks like the graph turns around. Well, turning points are just where that graph is allowed to turn around, and this property says, hey, if you have a degree of n, you've got at maximum n minus 1 turning points. And so the problem isn't asking you for a whole lot. It just says determine the max number of x-intercepts and the max number of turning points. So we look at the highest degree, which would be the leading term. And we say the degree is 9, which means max x-intercepts is, you're probably yelling at the screen right now. I'd missed it. Look at that degree. The degree is 12. I'll leave that in so you can see everybody makes mistakes. I made a mistake. It's okay. It's just important to go back and check your work so you see when that happens. So the degree is 12, which means max intercepts is 12. And that means that the number of turning points is at most 11. Degree, 12. Number of max intersections, or max x intercepts, is 12. Number of turning points, most 11, because we subtracted 1 from it. If you were yelling at your screen that I was missing the degree, good job. All right, let's move on to try at 8, where it asks us a pretty simple question. It says, what can we conclude about the polynomial represented based on its intercepts and based on its turning points? Well, let's look at intercepts, and we see we have 1, 2, 3 intercepts. Let's look at its turning points. We see we have 1, 2, and we know the shape of this because we've been looking at our toolkit functions. So a good guess is that our degree is based on the intercepts, 3, degree equals 3, and our max turning points is 2, which falls in line with 3 minus 1 is 2. And so a good guess or a good conclusion about this is that the degree is 3, which means it is cubic. And last but not least, we are given a function and we're asked to find everything we possibly could. And so I want to show you a little shortcut because they've already factored this function for us, and we can use that to make our lives a whole lot shorter. So when a function is fully factored for us, we can jump straight to x-intercepts because it's not too crazy. We look at each term and we say, okay, what if we set this term equal to 0 will yield x? So we look at this term and we say, oh, if we plug in 2, we'll get a 0 for the whole thing. If we plug in -1, we'll get a 0 for the whole thing. If we plug in 5, we'll get a 0 for the whole thing. That comes from that zero product property from back in the day. All right, so we got ourselves an x-intercepts. We got x-intercepts of 2, 0, -1, 0, and 5, 0. X-intercepts. Notice they didn't give us a y-intercept there, so we're still going to have to find that. That's okay. Maybe we'll do that next. Next thing we'll do is y-intercept. If you remember how to do y-intercept, you just plug in 0. So we're going to plug in 0. We're going to get 0.2 times -2 times 1 times 5, which is going to get us 0.2 times -10, which if you move the decimal over one time, you get -2. So you get the point 0, 2 as a y-intercept. So we got our y-intercept, we got our x-intercepts. We can look at end behavior by looking at each of the first terms. So in looking at each of those first terms, I'm going to look at, I might move this a little bit so we can see. Oop. Actually, let's just move this down. All right, so if we look at each of those first terms, we are going to see that distributing that 0.2 to the first term will yield us a 0.2x, and to the next term will yield us an x squared, and then to the next term will yield us an x3. So if you just look at the first terms of each factor, you can get your leading term without doing all of the foiling for 3 different equations. Your leading term is going to be 0.2x3. Nice little shortcut to get to your leading term, which tells you the end behavior looks like this, ... from up above. Remember, it's odd, so it looks like a line going down and up. And it's positive, so it looks happy. It looks like a bank account going up. So we got ourselves the end behavior of as x approaches -infinity, y approaches -infinity because it's going down. And as x approaches infinity, y approaches infinity. Yay. And last but not least, the number of turning points. Or they probably should say the max number of turning points, though if we were to graph it, we could probably find the real number of turning points as well. The max number of turning points, because we've got a degree, I'm going to highlight it right here. We've got a degree of 3. We know we have a degree is equal to 3, which means max turns is equal to 2. And so the max number of turns we have is 2, and if we were to graph each of these intercepts, we could see that in fact is 2. If we were to graph -2, or positive 2, +2, -1, and a +5 way out here, we'd see that in order to accomplish a down on the left and up on the right, we would definitely have to have 2 turnarounds somewhere. So the max turns is indeed 2. It's not just a max turns, that's the actual turns of 2. All right, so that's basically all we need to know about polynomials. If you would, go through the exercises in the text and the homework problems and make sure you're really practicing everything that you can to prepare yourself as best as you can for Chapter 5 as we approach the test at the end of the unit. Thank you for watching this far, and I will see you next time.